Alright, it's time to finish up section 3.4, zeros of polynomial functions. And we're going to start today with the fundamental theorem of algebra, the FTA. The fact that a polynomial equation of degree n has n roots is a consequence of a theorem proved in 1799 by a 22-year-old student named Carl Friedrich Gauss in his doctoral dissertation. The result of this is the fundamental theorem of algebra. And what this theorem says, if f of x is a polynomial of degree n, where that number is greater than 1, then the equation f of x equals 0, if we set it equal to 0, it has at least one complex root. Now remember, complex does not necessarily mean imaginary. You could have 3 plus 4i, that's a complex root. Or you could have 3 plus 0i. That's also a complex root. It's written in complex form, but the 0i means nothing, so that's the same thing as just writing the number 3. Since it's a video and you cannot ask questions, here is a question the video is asking for you. Do all polynomial equations have at least one imaginary root? No. As you read the fundamental theorem of algebra, don't confuse complex with imaginary and conclude that every polynomial equation has at least one imaginary root. Yeah, and that's kind of what I guess I spoiled the great question with what I was talking about before. All right. The linear factorization theorem. Linear means line. In example 5, we found that this polynomial has these as a solution set, 2 and negative 2 plus and minus I root 2, where the 2 is a repeated root of multiplicity 2. The polynomial can be factored over a complex non-real numbers as follows. So here's the polynomial we started with, and then here are its 4 factors, 1, 2, 3, 4. This fourth degree polynomial has 4 linear factors. Notice all the x's in here are x to the first power. So each factor by itself is a linear factor. This is formally stated as the linear factorization theorem. If we have this polynomial where n is greater than or equal to 1, so it's degree 2 or higher, the leading coefficient is not 0, then we can factor it like this. F of x is equal to, there's going to be some constant out here, maybe some coefficient, and then we have our linear factors, x minus c1, x minus c2, dot, 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 x minus c sub n, where these c values, c sub 1 and 2 and so on, are complex numbers, possibly real and not necessarily distinct. In other words, an nth degree polynomial can be expressed as the product of a non-zero constant and n linear factors, where each linear factor has a leading coefficient of 1. So here in example 6, we are going to create a polynomial given set parameters. So find a 4th degree polynomial function, f of x, with real coefficients that has the following zeros, negative 2, 2, and I. And then they also tell us that f of 3 is equal to negative 150. This helps us find our leading constant or our leading coefficient of this polynomial. And they've also given us a clues to the roots. What we're going to do here is sort of work backwards from finding the zeros. We know we have zeros here at x equals 2, at x equals negative 2, and at x equals I. Let's set each of these to equal to 0. Here I would subtract 2 from each side. So now it's x minus 2, and that's equal to 0. And here I would add 2 to each side. X plus 2 is also equal to 0. And for the I would subtract 1 from each side. X minus I equals 0. And remember at the end of the last video, after example 5, we had properties of these roots. And remember that the imaginaries come in complex conjugates only. So if x minus I is a factor, then x plus I must also be a factor. So here are our 4 factors. X minus 2, x plus 2, x minus I, x plus I. So we're getting close. Our function f of x, it's going to be written as those 4 factors multiplied out, but don't forget there could be a constant at the beginning, and I think they used a sub n. Yeah, right here, a sub n. So there's some constant here we haven't figured out yet, but we know after that we multiply all our factors, our x plus 2, our x minus 2, our imaginaries, x minus I, and x plus I. All right, let's start to work this out and FOIL. If I FOIL out this sum and difference, I get x squared minus 4. If I FOIL this out, I'm going to get x squared minus I squared. And remember, I squared is a negative 1, so that would be x squared minus a negative 1, which turns into a plus 1. And we still have our a sub n at the beginning, and this is some function we're trying to find, f of x equals that. Let's FOIL a little more. So it's still f of x equals. We have our unknown coefficient, and let's FOIL this out. X squared and x squared is x to the 4th. And then we're going to have plus an x squared and a minus 4x squared, which is minus 3x squared. And then negative 4 and 1 multiplied to negative 4. Now this is where that other little clue comes into play. F of 3 is equal to negative 150. So f of 3 is going to be this unknown constant. Now 3 goes in for all the x's. 3 to the 4th minus 3 times 3 squared minus 4, and the whole thing is equal to negative 150. So let's work in the parentheses. 3 to the 4th is 81, I believe, minus 3 squared is 9 times that is minus 27, and then a minus 4, and that's equal to a negative 150. Okay, and if I work in the parentheses, if I combine the two negative numbers, the minus 7 and the minus 4, this becomes a minus 31. 81 minus 31 is 50. A sub n, that unknown number, times 50 equals negative 150. So, of course, divide both sides by 50. This unknown number, a sub n, is negative 3. Now, I erased it, but you can go back up in your notes to where we had this line, f of x was equal to a sub n, and when we first unfoiled everything there, we had our x to the 4th minus 3x squared minus 4. Well, now we know that that a sub n is a negative 3. So I'm going to put a negative 3 here and distribute. And here's our final answer, our 4th degree polynomial, negative 3 x to the 4th plus 9x squared, and then the negative 3 to the negative 4 becomes a positive 12. So we found a 4th degree polynomial, 4th degree, 4th power. Real coefficients of 2, negative 2i, and negative I would be that if we factored it down, and we know it would work because we sort of did this backwards, and we built the factors, and then we folded them out to create the polynomial. And we could double check and plug a negative 3 in for all these x's, and a negative 150 should come out. You know, when we found that negative 3 and distributed it, we made sure that that would be the case. All right. I believe this is the last topic for this section of the chapter, Descartes' rule of signs. Because an nth degree polynomial equation might have roots that are imaginary numbers, we should note that such an equation can have at most n real roots. Descartes' rule of signs provides an even more specific information about the number of real zeros that a polynomial can possibly have. The rule is based on considering variations in signs between consecutive coefficients. For example, the function f of x equals 3x to the 7 minus 2x to the 5th minus x to the 4th plus 7x squared plus x minus 3 has 3 sign changes. Notice our first term is positive, then we go to negative, so right there we have our first sign change. And then it goes from negative to negative, stays the same, and then from here to here, negative to positive, sign changed again. Then there was another positive term, term, and then positive went to negative. So here was another sign change. So it says here this function has 3 sign changes. Let's see what this rule of signs says about that. Descartes' rule of signs. Here is our polynomial. Polynomial with real coefficients. The number of positive real zeros of the function is either the same as the number of sign changes or less than the number of sign changes of f of x by a positive even integer. So here we had 3 sign changes. So this polynomial at most can have 3 positive real zeros or a positive integer less than that. So what's 3 minus 2? 1. But yeah, with the 3 minus 2 because it was a positive even integer. Less than that number of sign changes by a positive even integer. So you just keep subtracting 2's out until you can't go any lower. So here we can have 3 sign changes or positive real roots. If we had a long polynomial with 9 sign changes, you could have 9 real roots, or 2 less than that, 7 real roots, or maybe 5 real roots, or 3 real roots, or maybe 2 real roots, or 1 real root. You know, you just keep subtracting 2's until you can't go any lower. Okay, now that was the positive real zeros. You can also get an idea of the number of negative real zeros. First, you would run a negative x through the function, find f of negative x, and then you'd count those sign changes. Those would be the number of negative real zeros. And you could also say that number or less than that number by a positive even integer. Let's try it out. And notice this is just for positive real zeros. So here's our first polynomial. I see 1 sign change here, and then a negative, negative to positive, another positive to negative. So there were 1, 2, 3 sign changes. What can we conclude? 3 positive real zeros. That's supposed to be an E. Zeros. That's an S for positive. Or 3 minus 2 is 1 positive real 0. All right, next one down. Positive 4 to positive 2. Oop, we got a sign change there. And then from negative to positive, we do have another sign change, and then all the rest are positive. So we had 1, 2 sign changes. So that tells us there are 2 positive real zeros. That's supposed to be an E. The pen is not being very cooperative today. Or subtract 2 from that, 0 positive real zeros. All right, last one, negative to negative, and then negative to positive, and then positive to positive. Looks like there's just 1 there. 1, so we only have 1 positive real 0. You know, if we try to subtract 2 from that, an even number, we'd wind up in negative land, and that doesn't work. If we wanted to find the number of negative real zeros, let's just do that for the first one. If we want to find the negative real zeros, we would do an f of negative x. And let's see here. Odd exponent, so the negative would be multiplied 7 times, and it would result in a negative 3x to the 7th. Because this is also a negative odd, that negative would come out front and hit this and become a plus 2x to the 5th. Plug it in a negative here, and then multiplying it 4 times would leave it the same, so that's a minus x to the 4th. Same here, we'd square the negative x and it would become positive and leave that term alone. This plus x would become plus a negative x or minus x and then a minus 3. Let's count those sign changes. Here's 1, and then 2, 3, 4. So since we found f of negative x, there were 4 sign changes, so there would be 4 negative real zeros, or 2 negative real zeros, or 0 negative real zeros. Alrighty. Example 7, determine the number of possible positive and negative real zeros. Okay, make this pretty quick. Positive. Here's f of x. How many sign changes? 0 sign changes. And that implies 0 positive real zeros. Okay, let's investigate the negative possible real zeros. To do that, we want to find f of negative x. And if I just plug negative x's in where all the x's were in the original function and simplify, we'll have f of negative x. So here the negative is cubed, so it'll come out as a negative x to the third. Here we square the negative away, and then we still have our plus 2. Plus 5 times minus x, the minus will hit that plus, and that'll be now become a minus. We got our plus 4. So let's see. Here's a change. Here's another change. And here's another change, 3. So there are 3 possible negative real zeros. Ooh, possible. You know, that POS almost looks like the positive there. 3 negative possible real zeros. Or 2 less than that would be 1 negative real zeros. Ooh, and then, yeah, what does that tell us about this here? You remember we were trying to solve these things and, you know, figure out what factors are going to work. If I'm looking at the possible zeros here, I got a 1 as a leading coefficient, 4 as the constant. What are the factors of 4? Plus or minus 1, plus or minus 2, plus or minus 4. When we first tested for possible positive real zeros, we found out there were 0 positive real zeros. There's not a chance of any positive real zeros. So we can eliminate all these positive roots. If I'm going to start guessing and checking with synthetic division, using Descartes' rule of signs, we can throw out the positive roots. Here we know it's going to be possibly one of these negative roots. So we could save ourselves a bunch of time by eliminating some bad paths to take that we might otherwise try. And since we were talking about it, let's try that out even. What did we get to here? So negative 1, 2, and 4 are our possibilities. Let's start out with negative 1. Why not? Best place to start. We know positive 1 won't work. We bring down our coefficients for synthetic division. We multiply and add, multiply and add, multiply and add. Look at that. No remainder right off the bat. We have reduced our polynomial down by a power, so now it's x squared plus x plus 4, and that's equal to 0. And the factors of 4 that add up to 1 will not work. I would probably lean toward the quadratic equation on this one. And remember, we did pull out a negative 1. I'll start my list of roots over here. And we would have a is equal to 1, b is 1, c is 4. So we have negative b plus and minus the square root of b squared minus 4 times a times c, all divided by 2a. So that's a negative 1 plus or minus, we got a 16 there. 1 minus 16 is negative 15, and that's all over 2. So negative 1 plus or minus, at least we can bring out the negative as an I root 15 over 2. So that would be our other 2. Again, the plus and minus, you know, it's 2 combined into 1. We'd have a negative 1 plus I root 5 over 2, and also a negative 1 minus I root 5 over 2. So again, using this rule of signs can at least eliminate some wrong turns in the guessing and checking with synthetic division. 2 for you to try on your own. The first one is make the polynomial. The second one is determine those possible positives and negatives. And this one you don't have to, you know, sort of solve it like we did in that last example. All right, we have zeros. It's a third degree polynomial. One of our zeros is negative 3, and the other is I. But remember, if I is a solution, so is negative I. So if I set these to 0, I would add 3 to each side. X plus 3 is a factor. Here I would minus I from each side. X minus I is a factor, as is its conjugate twin. X plus I is a factor. And remember, there is some unknown a sub n here. Let's FOIL. Of course, the easy way to go is to start off with the x plus and minus I, and that'll FOIL out into x squared minus I squared. I squared is a negative 1, so that turns into x squared plus 1. And then we can further FOIL that out. Oop, a sub n times. First times first, x to the third. Our next would be a 3x squared. Outers would give us a plus 1x. And 3 times 1 is 3. Okay, we're getting somewhere. Now it's time to work on that a sub n. What is our coefficient there? Well, they gave us the clue f of 1 is equal to 8. F of 1 is equal to this with 1's in for all the x's. Plus 1, and we set the whole thing equal to 8. So we have our a sub n times 1 plus 3 plus 1 plus 3 is 6 plus 2, or 8, and that's equal to 8. If we divide both sides by 8, we get a sub n is equal to 1. So this a sub n is just a 1, which means we don't even need to put it there. Our third degree polynomial is f of x equals x cubed plus 3x squared plus x plus 3. And there we are. Okay, number 7, our rule of signs. We'll start with the positive possibilities. Positive. How many sign changes? 1 sign change, 2, 3, 4. 4 sign changes means there's going to be 4 positive real zeros, or 2 positive real zeros, or no positive real zeros. So for positive, there's either 4, 2, or none. Let's check negative. F of negative x. Well, let's see, a negative to the 4th stays positive. Here it'll be a negative to the 3rd, which will turn that into a plus. The x squared will square the negative away, and it'll stay a 71x squared. Here the negative x will turn that negative into a positive, so now it's plus 154x. And nothing changes with the constant. So here, how many sign changes? None. 0 negative real zeros, and that's it. We know there's none. So if we were going to list all the possible factors here, and the possible factors of 120 would be positive or negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 20, 30, 40, 60, 120. Positive and negative of all those. By Descartes' rule of signs, we can eliminate all the negatives. So we would only start guessing and checking on all the positive possibilities there, which would save us maybe some considerable time. For homework, there you go. Enjoy.